You're driving your car and you want to go up this hill and down the other side. The problem is your car's quite old and it can only go at 15 miles per hour up the hill. When you get to the top of the hill, you ask the question, how fast do I need to go down the other side to average 30 miles per hour? It's quite a nice question to ask. The answer might shock you though, and to get to the answer, first of all, we need to think about distance and speed and how they're linked together. So we should be thinking of this formula triangle straight away. So speed is distance travelled over time. Speed, distance and time. And a nice triangle like that. And we'd like to think in terms of time for this problem, and you'll see why in a second. So coming from our formula triangle, we get time is distance divided by speed. So distance over speed. This is going to be the most important equation for us in this problem. Let's think about how to use it then. So first of all, if we think on a larger scale, for our entire question, our whole 2 miles, so all the way, my line's a bit wiggly, but for my whole 2 miles, I'd like to average 30 miles per hour, and this distance is 2 miles. So if I know my speed and my distance, I can work out the time that should take me. And let's call this time our total time. That should be the time for the entire uphill and downhill. And our total time is going to be the distance 2 over the speed, which is 30. That's what we want to average. So 2 over 30, that's the same as 1 over 15. And our units for that, because it's miles per hour, we'd have 1/15 of an hour. And actually turning that into minutes is more useful. That gives us 4 minutes. That's our first useful thing then. Our whole journey should take us 4 minutes. Well, now let's start thinking about some other stuff we already have. And it's this part here that's going to help us. We went uphill at 15 miles per hour and it took us 1 mile. So let's use this same formula. Time equals distance over speed. And we'll just call this our T. We could call it T1. The first part of our journey, just the uphill. Well, the distance is 1 mile and the speed is 15 miles per hour. So we've got 1 over 15. Well, again, that would be in hours, so this gives us 4 minutes. Put here 4 mins. Okay, something's not good about our 2 answers so far. It took us 4 minutes to get to the top of the hill at 15 miles per hour. And if we want to average 30 miles an hour for our whole journey, the whole thing should take us 4 minutes. So what this tells us is that we could think of this, the downhill, as T2, because this is the second part of our journey. And how much time is left over for T2? If it should take 4 minutes for the whole thing, it already took us 4 minutes. Well, this should take us 0 minutes exactly. And that's a real problem. Because if we then think about linking this time, 0 minutes to go downhill, and think about the speed, well, speed is distance over time. So the speed to go downhill is going to be the distance, 1 mile, divided by 0. And that just doesn't work. You can't do 1 divided by 0 and get an actual speed out. All we can say is that the speed going downhill would have to tend to infinity. I really like this problem because it's not an intuitive answer. At first glance you think maybe it should be 30 miles per hour or 45 or something sensible, but no, you've already used up all your time for the 4 minutes going uphill. You have to go infinitely fast. If you can put this, it tends to infinity. You'd have to go infinitely fast on the other side to ever hope to average 30 miles per hour. In the second part of this video, we're going to look at this problem a little bit more generally. And that means us switching from thinking, how fast do we need to go on a downhill to average 30 miles per hour, to now averaging v miles per hour. And v can just be any number that we like. I hope by looking at this we'll shed some more interesting light on the problem. So then, thinking about averaging v miles per hour, we're going to use our formula triangle to decide the most important equation for us, and it's how the overall speed and downhill speed link to each other. Let's start off then with something that might seem really obvious, is that the time taken for the journey in total, let's call that t, well, that's just a sum of two smaller times. And we've got our time taken to go uphill, let's call that t1 for the first part of the journey. And the time taken to go downhill, that's t2 for the second part. So t equals t1 plus t2. What we're going to do now is look at t in terms of distance and speed. So distance divided by speed for the whole journey, for t on the left, it's 2 miles. And the speed, well, that's v, isn't it? That's not decided yet. So we just have to call it 2 over v. t1 is for the first part of the journey. So distance on the first part was 1 mile. And the speed for the first part was 15. So we've got 1 over 15. And for t2, well, the distance again is 1. And the speed for the second part of the journey, we need to actually give ourselves a new variable here. We're going to call it v2. So that's the speed for the downhill, the second part. Great, this looks pretty good then at the moment. We've got 2 over v, our overall speed, is 1 over 15 plus 1 over v2. What we like then is to understand these as formulae in terms of each other. So I like a formula for v and v2 in terms of the other one. To do that, we need to first of all combine these two fractions together and then do some rearranging. Let's go for it. We've got 2 over v on the left, and on the right hand side we need to give these a common denominator. So we're going to get 15, chalk snapping, 15v2 on the bottom, and on the top we're going to get v2 plus 15. And that just comes from multiplying this fraction by v2 and this fraction by 15. Well, now we've got one fraction on either side, we can just flip these at this point. So we can say, well, v2 equals 15, oh sorry, this should just be v. v over 2 equals 15v2 over v2 plus 15. Can you see, I've just taken the reciprocal of each of these fractions. Moving over to the top here then, let's get rid of this 2 on the bottom to just have v equals 30v2, because we've multiplied everything out by 2, 30v2 over v2 plus 15. Okay, well that's quite nice, but actually we quite like v2 to be the subject. It's going to be more helpful for us later. So let's rearrange this thing to make v2 the subject. First of all, multiplying out by v2 plus 15. And when we do that, we'll get v2 plus 15v equals 30v2. Next step would be moving our v2's to the same side. So we've got v2 brackets, and we're factoring out of v minus 30. because this moves over to the other side, equals minus 15v. And then we want to divide by this v minus 30. But actually, being a bit smarter, we can divide by minus 1 lots of v minus 30. And we take care of this minus 15 then. So we're going to get v2 equals 15v over 30 minus v. You could check that if you like, it should all come out nicely. This is what's most important for us then. v2 as a function of our overall average speed. This formula is going to be so useful to us because if I tell you, oh, I'd like my average speed to be 20, well, we can substitute 20 in here to work out v2 or the downhill speed. That's what we're going to do next to explore this problem a bit further. Okay, we've started a new board, and for this part of the video, we're thinking more about v2 or the downhill speed as a function of our overall average speed v. We just found this equation or derived it, 15v over 30 minus v. First of all, let's do a bit of a table of values and think about how these two interact with each other. So we've got our v and our v2, overall speed and our downhill speed. Thinking of some interesting numbers then, well, what if I wanted to average 20 miles per hour for my whole journey? How fast would I have to go downhill to average 20? And if we just put the numbers in, well, v2 will need to be 15 times 20, which is 300 if I can do multiplication, over 30 take away 20. So that'll be divided by 10. 300 divided by 10 will be 30. So in other words, to average 20 miles per hour, I need to do 30 going downhill. Let's think of another interesting number then. What about if we wanted to average 25 miles per hour? We're slowly creeping closer to 30 here. And what I would have to do would be 15 times 25, which I'm going to need to write down. So v2 will be 15 times 25 over 30, take away 25. And let's think what that gives us. Well, 15 times 25 over 5 we're going to have. So 15 times 25 over 5, that's just going to be 15 times by 5, because we can see a 5 cancelling out. So 75 is our answer. And that starts to get interesting here, because to average 20, 30 seems pretty sensible. To average 25, you need to be going 75 on the downhill. That's really fast to not change your average speed by that much. And actually from here, this problem starts to get weirder and weirder as you go. So if we rub that one off, let's try another. We're still creeping closer to 30. And if we just change, because my chalk's running a bit low, let's try a weird one, like 29. If you want to average 29 miles per hour, how fast do you need to go on the downhill? Well, let's try it. So v2 would be 15 times 29. And on the bottom, we would have 30 take away 29. Thinking about what that's going to give us then. Well, 15 times 29, that's going to be 435. And on the bottom, 30 take away 29 just gives us 1. So to average 29 miles per hour for the journey, you need to be going 435 miles per hour on your downhill. Can you see the numbers seem to get spiraled out of control here? 20 miles per hour average, you only need to do 30. For 25, you needed to do 75. For 29, you have to do 435. Let's keep going a bit closer to 30 then. What if we wanted to do 29.9 miles per hour? Because this is still possible. So 29.9. Well, if we put this into our formula for V2, V2 would be 15 times 29.9. And on the bottom would be 30 take away 29.9. Well, thinking of these numbers then, 15 times 29.9, I think it should be what, 450 take away 1.5, so 448.5. And on the bottom, we're going to have 0.1. And actually, what's the key part with what we've seen is as our number becomes closer and closer to 30, the top of our fraction gets closer and closer to 450, because that would be 15 times 30, but the bottom of our fraction becomes uncontrollably small. It went from being 10 to 5 to 1 to 0.1, and that sends our number skyrocketing up. So 448.5 divided by 0.1, well, that's the same as timesing by 10, isn't it? So we're going to get 4,485 and 85. So adding that in, 4485. Let's make this table look slightly nicer. These are some key findings for us then. We can see this pattern here, that as the velocity that we would like becomes closer to 30, up to 29.9, our downhill speed, V2, has to become infinitely large at some point when it gets to 30. You can see 30, 75 still doable. I don't know any cars that can go this fast, and that's just insane at that point. If we wanted to go to 29.99, we'd see this thing keep on going up and up and up. In this final part of the video, I would just like to graph our function that we've derived, which is V2, our downhill speed, in terms of V, our total average speed. Just so we've got a really clear picture of exactly how this operates. These were the values, by the way, that we just found before. So if we want V to be 20 on average, we need to do 30 miles per hour downhill, and so on. First of all then, let's consider what this graph might look like. And actually we can reason that we only need to draw the positive quadrant for this graph. And here's why. Our speed has to be positive for V2. So we're not worried about negative speeds for this part, but more importantly here is that our V can never be more than 30. We've already established that you'd have to go infinitely fast to average 30 miles per hour. So it just doesn't make sense to think about going any faster than that. What that means then, because V is less than 30, 30 minus V has to be greater than 0. And because V is positive, and this is greater than 0, our V2 has to be positive as well. We're just all positive. First thing that we should put on our graph is, well, we want V2 as a function of V. So that means V2 is going to take the place where Y would usually go, and V, our overall speed, is going to take the place where X would normally go. I wonder if we can use any values yet, or if there's one more important thing to consider. And if looking at the denominator gives us a clue, it's that, well, when V equals 30, the denominator goes to 0. That means we have an asymptote where our graph will go to infinity. So we should mark on our graph, let's say it's here. This is where V equals 30. That was our problematic point from our earlier problem. So V equals 30. We have to go infinitely fast there. We're going to just go right up there. Thinking about the behaviour of our graph, you can see that actually it's not that steep here, 30 to 75. is comparatively really not that steep compared to 435 to 4,485. So we're going to have this behaviour that definitely curves upwards, but we should maybe think a bit more about some other key points on our graph. And notably, something like, well, what if we set v2 to be 0 or v to be 0? Let's try if v was 0. So if v is 0, then v2, because obviously they're linked by this relationship, is going to be 15 times 0 over 30 take away 0. And that's definitely just 0. What that tells us, and this might make, intuitive sense, that if we would like our overall speed to be 0, we have to average 0 on the downhill. Yes, absolutely. Even though that doesn't, it feels almost wrong because we were going faster earlier, but that's what we have to do. We have to go 0 to average 0. We've got this point, and we're not going to cross our axes in any other place. So because we know the general behaviour has to look like an upwards curve, we're happy to just draw the rest in. We've got an asymptote at v equals 30, and we can imagine on there some points that we've already plotted. So this point would be 20, 30 as a coordinate. V is 20, V2 is 30. Let's just add one more on to see some more information that we put in. This could be 25, 75 as a coordinate. So 25, 75. Hopefully then, having built up this picture of how the graph looks, how it operates, the relationship between V and V2, that gives us a really clear and comprehensive answer of exactly why Einstein's original problem, averaging 30, was just unsolvable. You have to go infinitely fast. Looking back at the end, it's because that's the asymptote of the graph that links V and V2.